So as we move on with moments here, we're going to come across a new variety of question, and the main difference you're going to see here is that the center of mass, the place where we model the weight as acting, is not necessarily going to be in the middle of the plank. In the question itself, we're going to be looking for the phrase non-uniform. In most of the questions you've done up to now, there would have been the phrase uniform, which actually indicated and let us know that we should model the weight right at the center of the rod or of the plank. But now that it's non-uniform, we don't know that we're going to model it at the center. In fact, we know not to model it at the center, but we don't know exactly where we will model it unless the question tells you that it's a certain distance or it's a certain position. You may have taken it for granted that we model the weight at the middle, but it really comes down to the phrase uniform or the phrase non-uniform. So make sure you're actually reading through the question and looking for either of those two phrases. So when working with non-uniform planks, we're likely to be asked to find the position of the center of mass, or if we're told that, we'll be asked to find unknown weights or unknown lengths elsewhere. Now let's get into an example. So in this question here, we're told that Sam and Tasman are sitting on a non-uniform plank AB, which has a mass of 25 kilograms. The plank is pivoted at M. So I'm just going to model M, which is actually the midpoint, and I'm going to label the plank AB. The center of mass is at C, and AC is 1.8 meters. So I can label that on the diagram as well. So from A to C should be 1.8. So here's my C. If AC is 1.8 and AM is 2 meters, then I know that CM should be 0.2 meters. And remember, we want to try and label these individual distances. We don't want any overlapping length labeling. So individual lengths. All right. So Tamsin is sitting at point A and she weighs 25 G. She has a mass of 25 kilograms, but she weighs 25 G. We need to figure out where does Sam need to sit so that we have equilibrium. Well, Sam weighs 35 G, and at the moment I don't know how far away from B he should be, so I've labeled that as X. M to Sam should then be 2 minus X to make sure that MB still adds up to 2 meters. Okay, from here, I'm just going to add in the reaction force, and I'm going to add in the weight of the rod, which is 25 G. And at this point, we've got a fully finished model. Our diagram's complete. It has all the forces, all the distances. We can go ahead and solve using the strategies that we usually do. And those strategies are firstly to resolve vertically, so we can get an expression for the reaction force. Resolving vertically, I get reaction equals 85 G. And then I'm going to go ahead and take moments. Where am I taking moments from? I'm going to take moments from M, since that's the only support point, it's the only pivot point, which actually means I'm not going to use the reaction force. But just good practice to make sure that we get that in the first place. Clockwise moment is the 2 minus X multiplied by 35G. Anti-clockwise moments are 0.2 times 25G and 2 times 25G. Okay, just resolving these. Simplifying and isolating the X is going to tell me the distance that Sam should be sat away from point B. So as usual, so expand those brackets, collect like terms, make X the subject. So that gives us a value of X as 15 over 35, which cancels down nicely to 3 over 7. Now remember, in mechanics, we usually give our answers as decimals, and because we've used the value G, the acceleration due to gravity, which is a value to 2 significant figures in maths, we should then give all answers that follow from that also to 2 significant figures. Mark schemes allow 3 significant figures, but I'm going to recommend that you stick to the 2. Alright, so to answer the question finally, where should Sam sit? Sam should sit 0.43 meters away from point B. Okay, so moving on to another question. So there's just a bit more detail in this one, so make sure that you're reading all the way through. And there's no diagram. You already know that I like you to be able to produce your own diagram at each and every opportunity, regardless if you were given one to begin with, because you want to add to it and add a lot more detail than the original diagram may have. So this time we've got a non-uniform rod once again. It's 3 meters long and has a weight of 20 newtons. So we're already given the weight. It's already in newtons. It's in a horizontal position, resting on supports C and D. Okay, so let's get drawing. So we're drawing the rod AB. AC is 1 meter. So I know that this support of C is 1 meter away from A. We're also told AD is 2.5 meters. So actually, to get from C to D will be just 1.5 meters. So just be careful that you've done the subtraction there and we're labeling our diagram sensibly. Since we know the whole rod was 3 meters long, we know that over here dB is going to be 0.5. We've been told that the magnitude of the reaction at C is 3 times the magnitude of the reaction at D. So at this point, we're going to start with the smaller reaction, which is the one at D, and call it R. And at C, we'll call that 3R. 3 times bigger, it should be the larger of the two. Now, we've been asked to find the center of mass of this rod. So initially, we're just going to estimate where we think it might be. And I'm just going to place it in the middle of C and D. Right, so I'm just going to mark it off there. You notice I've rubbed out the 1.5. So there's the weight, 20 newtons. I'm going to call this distance from C to the center is X. So from the center to D is 1.5 minus X. So this unknown distance is what we're really looking for. Now that I'm happy, I've got a fully labeled model. My diagram's complete in all the aspects that I need it to be. I'm going to go ahead and use the 2 strategies we always use, resolving vertically and taking moments. So resolving vertically, I get 4R equals 20 newtons, so R equals 5 newtons. So I know the reaction force at C is 15 and the reaction force at D is 5. Let's go ahead and take some moments. You can choose, but I would like to choose C because at least I know I'm going to get an expression in terms of X right at the beginning of my equation. So the force times the distance for that clockwise moment, and that should equal the anti-clockwise moment, which is actually going to be 1.5. It's the whole distance from C to D times the reaction force. Expand and simplify from there. We already knew that R is 5, so 1.5 gives us 7.5. Working that through, we get a value of X as 0.375. Okay, so that's the distance from C to the center of mass. But this question actually asks us to find the distance from A. Make sure you go back and you read the question. I know some of us will be tempted to leave that as the final answer. But the distance from A is going to be 1 plus the 0.375. So altogether, 1.375 meters. So if you notice, in this question, we didn't need to use G. So we didn't use the approximated value, and we didn't have the stipulation of having to stick to either 2 or 3 significant figures. So I had a choice to actually be a little bit more accurate in my answer, and I've gone for 3 decimal places in this instance.